Hi everyone. In this video, I want to talk a little bit about functions of several variables. From your reading of 9.1, you know that these on the screen denote functions, very similar to what you are used to for single variable functions like y equals f of x. And for these single variable functions, when we visualize the relationship between all possible values of x and their corresponding output y values, we use the two-dimensional coordinate system by drawing the y-axis and the x-axis. So here's x and y, and maybe the graph of a function might look something like this. So every single point on the graph is corresponding to the relationship between some particular value of x and particular output corresponding to that input. So the domain of functions like this, let me use D to denote that. This is in the set of all real value, which we use the notation R like this. And of course, the graph of something like that, since it's consisting of all ordered pairs, so that the graph is in the two-dimensional space that we use the R2 to denote. Now, what makes it more challenging in this class is that what we want to visualize now sits inside of higher dimensional spaces. For functions of two variables, like this one right here, the input is an ordered pair x comma y, so the domain is inside of the two-dimensional space R2. If we graph the function for something like that, then each point on the graph is a point given by the input x comma y and the corresponding value of output. Say we're going to use the variable z4. So each point is going to be given by an ordered triple, which sits inside of a three-dimensional space that we use the notation R3 for. For functions of three variables, like this one right here, the domain of these functions, since these are going to be given by ordered triple like this, so it's sitting inside of R3, so the domains can be visualized. However, the graph of these functions, since it's going to require 4 different values, these are going to be sitting inside of four-dimensional space R4. So unfortunately, functions of 3 or more variables, we cannot visualize them anymore. So we will need to do other things to be able to understand these objects. Now let's focus a bit more on functions of 2 variables and their domains. Identifying the domains for these is similar to what you do for single variable functions. By that, what I mean is you need to focus on restrictions for possible input imposed by the functions. For example, let's say that you have this single variable function y equals square root of x minus 2. Now you know that when you have a square root function like this, the restriction in this case is that what's inside of the square root, the radicand, must be non-negative, meaning if I were to write that, it would be something like x minus 2. What's inside of the square root cannot be negative, so it would be greater than or equal to 0. Which, by the way, though, if I just solve this linear inequality you get the condition that x has to be greater than or equal to 2. So you know that the domain for this function is given by x is greater than or equal to 2. Let's go through these 4 examples that I have here, starting with number 1. Now this function number 1 is a polynomial function. So there's no restriction as to what kind of value that I can plug in to x or y. So the domain for this function is all possible ordered pairs x comma y. So in this case, the domain is going to be R2 itself. Number 2 is a square root function, just like we saw earlier. So we know that the restriction in this case would be that the radicand, or what's inside the square root, has to be greater than or equal to 0. So we can write the inequality x squared minus y has to be greater than or equal to 0. Or another way of writing that is by moving the y over, x squared has to be greater than or equal to y. Now in this particular case, we can actually sketch the region that's being described by this inequality. So let's draw this coordinate system. Here is x and the y here. And we know what this y equals x squared looks like. It's just the typical parabola. So it would look something like this. Sorry about my rough graph here, but this, let's say that this is the graph of y equals x squared. But the domain given by this for this function is that every possible ordered pair that would satisfy x squared is greater than or equal to y. So what that means then is that we need to look at all points that are on or below the graph of this function y equals x squared. So this would be the two-dimensional region consisting of all possible ordered pairs. So this would be the sketch of the domain for this function. Okay, number 3. This is a log function. So in this case, the restriction would be that the argument of log has to be positive, not non-negative. 0 cannot be included here. So the inequality that I can write would be x squared plus y squared minus 4. This needs to be strictly greater than 0 because it needs to be positive. But that means that if I rewrite this a little bit, x squared plus y squared has to be greater than 4. Now again, in this case, we can definitely sketch the region that's given by this inequality. So again, here is the x-axis, here is the y-axis. So I'm looking at this inequality, and if I were to replace that inequality by the equality, equal symbol, x squared plus y squared equals 4, that is going to be a circle centered at the origin of radius 2. So in this case, since that the boundary cannot be included, I am going to use the dashed line to indicate that this boundary cannot be included. And now this is because that the inequality is given by the strict inequality not greater than or equal to. But now, so in this case, these possible values of x and y has to give us so that this expression is bigger than 4, which means that everything has to be outside of the circle. So in this case, the region describing that the domain is going to be everything that is outside of this circle. not including the boundary that's given by that circle there. Number 4. Now this function is a rational function, so we know what the restriction for a function like this is. Essentially, whenever you have a fraction, we need to make sure that the denominator is not 0. So I can basically write the condition as the denominator x minus y cannot be 0. Well, what does this mean then? So this means that the x cannot equal to y. So again though, geometrically, if I were to visualize the set of all pair x comma y that is going to satisfy this relationship is going to be pretty much everything on the two-dimensional coordinate system. So here is x and y. And this is going to be pretty hard to actually draw this, but every point where x actually equals to y is going to be on this line given by y equals x. So the domain is going to be every possible points that are not on this line. So you need to actually don't depend too much on my drawing here, but if I were to just describe this, the set of all ordered pair x comma y that are not along the line y equals x. So that would be the domain for this function number 4. So these are the examples of functions of two variables and how you might think about identifying their domains.